In this illustration, we intend to simulate the vertical stress in a layered soil caused by a circular loading in the Abaqus software. The soil is composed of 4 layers, the first layer of which is asphalt layer with a thickness of 0.25 meters. The second one is base layer with a thickness of 0.5 meters. The third layer is sub-base layer having a thickness of 0.5 meters. And the last layer is existing soil layer, the thickness of which is 48.75 meters. The loading area is a circle and a pressure equal to 10 kilopascal is applied to it. In the right picture, the diagram of vertical stress for different depths has been drawn. Actually, we intend to simulate the example 3.8 from some Helvani book in the Abaqus software. Here you can observe the geometric shape of soil, in which the soil has been considered in form of a cylinder with a height of 50 meters and diameter of 100 meters. As it is observed in the picture, the properties of each layer is quite different with another one. I will enter the Abaqus software for simulation. I will click on Create Part. Here I intend to create geometric shape of soil. I will select the modeling space as axis symmetric, select deformable and shell, and continue. I'll draw square. As described in the book, the soil has been considered in form of a cylinder with a diameter of 100 meters and height of 50 meters. So I will enter the height of soil equal to 50 meters, radius of soil equal to 50 meters too, and click on Done in this manner. As it can be observed in the picture, the soil is composed of 4 layers. The thickness of the first layer is 0.25 meters, the second layer is 0.5 meters, the third layer is 0.5 meters, and the fourth one is 48.75 meters. I will click on Tools menu, then on Partition, and then click on Face and Sketch in order to create layers. I'll click on Offset Curves, select this line, and Done. I will enter offset distance as 0.25 meters. Then I'll click on Flip and OK. Then I will select this line, Done, enter offset distance equal to 0.5 meters and OK. I'll select this line again, Done, enter offset distance as 0.5 meters and OK. And finally click on Done. In this manner, the soil would be composing of 4 layers, which can be observed here. In the next step, I'll enter Property module. Here, since the properties of each layer is quite different with those of another layer, we should define 4 materials accordingly. I will click on Create Material. Here I intend to define the properties of asphalt layer. I will select Elasticity and Elastic from Mechanical menu, the Young modulus is equal to 7 multiplied by 10 to the power of 11 Pascal, and the Poisson ratio is equal to 0.3. I will click on OK, then on Create Material. Here I intend to define the properties of base layer. I'll select Elasticity and Elastic from Mechanical menu. The Young modulus is equal to 7 multiplied by 10 to the power of 10 Pascal, and the Poisson ratio is equal to 0.3, and OK. Again, I'll click on Create Material. Here I intend to define the properties of sub-base layer. I will select Elasticity and Elastic from Mechanical menu. The Young modulus is equal to 7 multiplied by 10 to the power of 9 Pascal, and the Poisson ratio is 0.3, and OK. I will click on Create Material again. Here I intend to define the properties of the last layer. I will select Elasticity and Elastic from Mechanical menu. The Young modulus is equal to 7 multiplied by 10 to the power of 8 Pascal, and the Poisson ratio is equal to 0.3, and OK. I will click on Create a Section, Solid, Homogeneous, and Continue. Here I will select Asphalt layer and OK. I will click on Create Section, Solid, Homogeneous, and Continue. Here I will select Base layer and OK. I will click on Create Section, Continue. Here select Sub-Base layer and OK. Then I'll select Existing Soil layer and OK. I will click on Assign Section, select the first layer, Done, then select Asphalt layer and OK. I will select the second layer, Done. Here select Base layer and OK. I will select the third layer, Done. Then select Sub-Base layer and OK. Finally, I will select the last layer, Done, and then I will select Existing Soil layer and OK. If I select Materials here, you will observe that the color of each layer is different with that of another layer because the properties of them are different with one another. In the next step, I will enter Assembly Module, click on Create Instance and OK. In the next step, I will enter Step Module, click on Create a Step. Here select Static General and Continue. The analysis will be in non-linear form. I will enter initial increment size equal to 0.1 and OK. I will enter Load Module. Here I will enter Part Module. As described in the book, the loading area is a circle with a radius of 0.5 meters, which can be observed here. Well, I will select partition from the tools menu, then face and sketch, select the whole of the soil and done. I will draw a vertical line in this manner, enter the distance between these two lines as 0.5 meters and click on Done. I will enter Load module, click on Create Load, select Pressure and continue. I will select this surface, Done. As described in the book, a pressure of 10 kilopascal will be applied to the top surface of the soil. I will enter the quantity of pressure equal to 10,000 pascal and OK. In the next step, I'll click on Create Boundary Condition, select Displacement Rotation from here and continue. I'll select the bottom of the soil, Done, and close the boundary conditions of U1 and U2 for it and OK. Again, I will click on Create Boundary Condition, select Displacement Rotation and continue, and select this surface, Done, and close the boundary condition of U1 for it and OK. In the next step, I will click on Create Boundary Condition, select Symmetry Antisymmetry from here and continue. I will select this line, Done. This line is axis of symmetry. Close the boundary condition of X symmetric for it and OK. In this manner, I will return to the Part module, select Partition from the Tools menu, then Base and Sketch, select the whole of the soil, and Done. Here I will draw a horizontal line. Consider the distance between this line and this one equal to 5 meters, and click on Done. Actually, as we intend to calculate the increase of stress for the range of height between 0 to 5 meters, we have built this partition on the model. Well, I will enter Mesh module, select Assign Mesh Control, select the whole of the soil, Done. Here select Structured and Quad and OK. I will click on Seed Edge, select these lines, Done, and enter the number of 2 elements for them and OK. Then I will select these lines, Done, and consider 4 elements for them and OK. Then I will select these lines, Done, and consider 4 elements for them and OK. Then I will select these lines, Done, consider 25 elements for them and OK. In the next step, I'll select these lines, Done, click on Single, then on Size. I will enter the minimum size as 0.25 meters and the maximum size as 7 meters and OK. In the next step, I will select these lines, done. Click on select, again select these lines and done. I will enter minimum size as 0.1 meters and maximum size as 6 meters and OK. In the next step, I will select these lines, done. Consider 4 elements for them and OK. In the final step, I'll click on mesh part and yes, in this manner. As you observe, fine mesh has been used in the area where the loading pressure is applied. I will enter job module, click on create job, continue, OK, and click on submit. The analysis was done successfully, so I'll click on result. The purpose of this analysis is to draw this diagram. Actually, we intend to draw the diagram having been marked out with a red arrow. In this diagram, a vertical stress has been calculated for different depths. First, I'll click on Tools menu, then Path, and Create, Continue, Add Before. First, I will select this node, then this one, done, and OK. In the next step, I will click on Create XY Data, select Path, and Continue. Here I will select Undeformed, tick on Include Intersection option. Here I'll select S22 or the same vertical stress and OK, and click on Plot. I will right-click on the diagram, Edit, select these two columns, copy, and paste them in the Excel software. The first column is depth, the unit of which is meter. The second one is vertical stress, the unit of which is Pascal. As you observe in this diagram, the unit of stress is kilopascal, so I will divide all the quantities of this column by 1000. So the unit of stress will be converted from Pascal to kilopascal. This column is vertical stress, the unit of which is kilopascal. I will click on this diagram from the Insert menu, right-click, choose a Select Data option, click on Add, select this column as the X-axis and this one as the Y-axis, and click on OK. Here I'll click on Values in Reverse Order option, then click on Maximum Axis Value option, and I will do the same for vertical axis in this manner. The diagram having been drawn in blue color is the one obtained from the Abaqus software. As you observe, the results having been gained from the Abaqus software are quite concordant with those obtained from Sam Helvani book, and both diagrams have been set on one another concordantly.